Hello, everybody. Welcome to the ICSI 2020. This is the High-2 security session. We have 6 research papers, 4 full papers, and 2 nears papers. So our first presenter for today is Valentin Wustholz, who is a researcher and consensus diligence. He's going to present us targeted gray box fuzzing with static look-aheads. Please, Valentin, the virtual stage is yours. Remember to unmute.
Hi, thank you very much for the introduction. So this is joint work with Maria Christakis from MPI SWS. So what is targeted gray box fuzzing? Well, let's look at classic gray box fuzzing first. Classic gray box fuzzing is an automated test case generation technique that uses code coverage feedback to guide the testing process. Now, the goal behind targeted gray box fuzzing is to focus on executions that reach target locations in the code. Examples would be newly added code or code that emitted static analysis warnings. Now, the main challenge with this type of fuzzing is that it's difficult to predict which inputs are close to target locations. And this feedback would be very useful to guide the fuzzer. So in this work, I present you a new type of analysis that allows you to compute such feedback for a fuzzer. And on the left-hand side, you can see a fuzzer. It takes a seed input, and it takes a set of target locations. And then it produces a test suite that is stored in a queue. And new elements are added to that queue when the corresponding input achieves new coverage. So when we add an input to the queue, we run our so-called look-ahead analysis. And this is an online static analysis that analyzes the input. And it produces feedback that can then be used by the fuzzer. So on the left-hand side, you can see, on the right-hand side, you can see the execution tree for a given input. And the path that is explored is in bold here. You can also see 2 target locations, Tx and Ty. Now, the goal of the look-ahead analysis is to compute the so-called no target ahead prefix. And in this case, that would be the prefix pi pre. Since once you reach the so-called split point pi, any path that follows this prefix will not be able to reach the target locations, Tx and Ty. The look-ahead analysis will also compute a set of so-called split points, pi and to p1. So how does this work on a high level? So the analysis basically searches for the first split point without targets ahead. And this works in 2 steps. First, we compute a post condition for the given path along the prefix pi pre that ends at the split point pi. And we use this post condition afterwards to run a more classical reachability analysis starting from the split point pi when assuming phi as the entry condition. So this, as you can see, this analysis is partially path sensitive because for the prefix, we actually just analyze straight line code along this path. So this partial path sensitivity helps to increase precision, for instance, because in the abstract domain that is used, you don't need to do any joins. We also are guaranteed that this prefix is actually feasible because the fuzzer just generated an input that explores it. However, since we run this analysis many times during the fuzzing process, we need to make sure that this analysis is fairly lightweight. So let's look at how this is integrated into the kind of classic gray box fuzzing algorithm. So here you can see the algorithm, and in this loop, the fuzzer picks an input that will be fuzzed, in this case I, and it assigns a certain amount of energy to it. This determines essentially how many times you will be fuzzing this input. So when you fuzz the input, you get a new input f, and then the fuzzer runs the input on the program to get a so-called path ID. This basically describes the path that is taken through the program. And if a new path has been encountered that you haven't seen before, the path or the input is added to the test suite, to the queue. So the first extension that we made in this work is to run our look-ahead analysis. And this happens here whenever a new input is added to the queue. And we use the feedback that is computed from this analysis to assign a more targeted amount of energy here. So let's look at this part in a bit more detail. So you probably observed that the queue, all the elements in the queue, all the inputs there, they have different path IDs. However, they may share the same no target ahead prefix. So essentially, this partitions the queue into different groups. And now when we assign energy, we assign more energy if one of the two following conditions hold. So either the input's no target ahead prefix was rarely executed, or any of the split points for this particular inputs were rarely executed. And the intuition behind this is to essentially reward the discovery of new prefixes and new split points. So this is partially inspired by fair fuzz. We also implemented this in a gray box fuzzer for Ethereum smart contracts, and that consists of two main components. First, there is the existing Harvey gray box fuzzer, which we extended, and which is part of the commercial MythX analysis platform. We also added a new component called Bran that is a lightweight abstract interpreter and uses constant propagation. This is used for the look-ahead analysis. In our evaluation, we evaluated this on 27 real-world benchmarks, and we were able to show that for 83% of the challenging target locations, the fuzzer was able to reach them significantly faster with this extension. We also saw a median speed up of 14x for reaching these locations. And the look-ahead analysis that we designed turned out to be very lightweight. On average, it was roughly 3 seconds per 1 hour of fuzzing. So to summarize, I've presented a symbiotic approach to targeted fuzzing using dynamic and online static look-ahead analysis. Thank you.
Thank you, Valentin, for your talk. So we have now 4 minutes for questions. Please, guys, write them down on the Slido chat. I think I'll start with the question myself in the meanwhile. Okay, we got some questions about your plans to publicize the tool. Is it available for people to use and start exploring?
Yeah, so there, as I said, there's 2 components to this. The static analysis component, which is called Bran, it's available on GitHub. I can share a link in the channel if you're interested.
Definitely, that would be cool.
The fuzzer itself is currently still closed source, since it's part of our MythX analysis platform, and I personally would like to make it available, but there's some basically business reasons why we haven't made that available yet. Yeah.
All right, thank you. We got another one. How do the results depend on the kind of target location? for instance, deep in program versus shallow targets?
Yeah, I mean, it's hard to say in general. So I guess the more deep they are, of course, you need to maybe run many different inputs to actually reach those like locations. However, essentially at each, like the deeper, the closer you get, essentially you will find new inputs. And then by running the look-ahead analysis again on those new inputs, you sort of gradually kind of should approach the target location. So yeah, and I think there also the path sensitivity helps, because essentially if you run like just static analysis from like on the whole program, basically it's going to be very imprecise typically. So yeah, I think that's basically would be my guess for this. Yeah.
Okay, thank you. I was wondering to which kind of software is this fuzzer applicable? Is it like only Ethereum contracts, or is it like broader in scope? What's your opinion on that?
Yeah, I think the current implementation is for Ethereum smart contracts, so it runs on the contracts bytecode. However, I think the general approach is could be applicable to any type of software. I mean, essentially, smart contracts are not that different from regular software. So, of course, it requires some sort of adjustments, like maybe the analysis would need to be a bit different. The abstract domain might need to be a bit different. So there's probably several like extensions or like tweaks that you would need to do. But yeah, in principle, I think it should work, like not just for smart contracts.
All right, thanks. So I think we are good with you. We can go on and continue with the next presenter, who is gonna be Yannick Nolle, who is a PhD student at University of Berlin. And Yannick is going to present us a paper about hybrid differential software analysis. Please, Yannick.
Thank you. Hi, everybody. My name is Yannick, and I'm going to talk about HiDiff, our hybrid approach on differential software analysis. This is joint work together with Corina Passeranu, Marcel Böhme, Yuqing Sun, Huang Lam Nguyen, and Lars Grunske. In our work, we are focusing on two different flavors of differential analysis. The first one we are taking into account is concentrating on two subsequent broken versions, and we are trying to find the differences between them. This is also called regression analysis, and it's one of the most common differential analysis types in software testing. For our flavor, we are considering only one program, but we are searching for different characteristics in this program. This is useful, for example, for the sidechain analysis, where we're trying to find secret-dependent paths. And here the idea is that we take two different secrets and then observe the program execution and search for differences with regard to the execution behavior of the side channel. And then another example would be the robustness analysis of neural networks, where we try to find two different but still very similar inputs which produce a different output of a neural network. So in this slide here, you can see an overview of our approach. What we essentially do is we combine fuzzing and symbolic execution. So fuzzing on the one hand side, we already heard something about it, is very good in finding shallow bugs. It's a very efficient input generation technique, but since it's using random mutations, it's very unlikely to hit very specific constraints in the program. So it's bad in finding deep program paths in general. Symbolic execution, on the other hand side, performs a systematic exploration, and it's known for its input reasoning abilities. But still it suffers from path explosion and complex and expensive constraint solving. So while the combination of fuzzing and symbolic execution in a sequential manner is already known, we perform it in a parallel manner, which means from time to time, both components will exchange interesting inputs and therefore amplify the exploration. And please also note that we perform a differential analysis, and here in general, we have to reason about multiple paths at the same time. In the next few slides, I will give you some overview about each stage in HiDiff. So let's start with the inputs. Of course, we take some seed inputs to drive the initial exploration. Here we need at least one input, but if you have an existing test suite, we also can incorporate all of these inputs. And then we take also the program under test for our inputs. Here we distinguish between fuzzing and symbolic execution. For fuzzing, we take the actual program and instrument it, for example, to measure the program coverage. And for regression testing, we take multiple program versions. For symbolic execution, we take a change annotated program. And here we differ between two different change annotations, change types. So the first change type would happen in the program code. This is something which we need for regression testing. And here we adapt and extend the change annotations by Palikariba et al. We introduced these change annotations to unify two program versions into one program version to perform an efficient symbolic execution for regression testing. For example, if you have an updated assignment, you can represent this change by adding this change function call, where the first parameter represents the old expression and the second parameter represents the new expression. The second type of changes happens in the input, and this is necessary for site analysis and also the robustness analysis of neural networks. And here we also apply the similar notion as this change annotation. So we also have this change function call, but now we do not represent old and new versions, but we have two inputs, which we then merge into one input. Then for fuzzing component, we call it differential gray box fuzzing. We built here on top of AFL, which uses a genetic algorithm to reduce new inputs. So it's a mutational fuzzing approach. And here the most interesting part for us is the mutant selection, which determines which inputs are kept for further mutations. And here we apply differential heuristics. So we would keep inputs which show some output difference or also decision history difference. With decision history, we mean the different branching behavior inside the program. And for side channel analysis, we also incorporate the cost difference with regard to the specific side channels, but also the patch distance for regression testing, which is important to guide the fuzzer into the changed areas of a broken code. And additionally, this process is also guided by branch coverage. The symbolic execution component is called differential symbolic execution. It builds on top of a dynamic symbolic execution inside symbolic pathfinder. The central data structure which we use is called a trie. It's a compact representation of a symbolic execution tree. And while I talked about mutant selection fuzzing, here in symbolic execution, I talk about node selection. So what you want to do is to want to pick a most promising node in the symbolic execution tree, which is not explored yet, and which we can use for further exploration. And also this process is guided by differential heuristics. As you remember, we have these change annotations for symbolic execution, and these change annotations specifically drive the decision history difference. And so this is the most important metric here, but we also incorporate the cost difference and the patch distance. And additionally, also this process is guided by the branch coverage. And then finally, the output of HiDiff will be a set of inputs which show some divergence. And we classify these inputs by the divergence, so for example, output difference or control flow difference. For the evaluation, we performed experiments in these three application scenarios: regression analysis, sidechain analysis, and robustness analysis of neural networks. And the goal here was to compare HiDiff with its components in isolation. And what I want to do in this slide here, I would like to give you a brief overview about the results which we observed for these experiments. So for regression analysis, HiDiff was able to classify all subjects correctly, which means that if there's a subject which actually has an output difference, HiDiff was able to identify at least one output difference. In contrast to its components, where fuzzing and symbolic execution was not able to identify all subjects correctly. Furthermore, HiDiff was able to generate significantly more output and decision differences for these subjects. For the sidechain analysis, HiDiff showed very good trade-off between symbolic execution and fuzzing, but there was no significant amplification of the exploration. The reason here is that differential fuzzing is already a very powerful tool for this context, and the combination with symbolic execution did not bring so much benefit besides the simple combination of the outputs. And the last scenario, the robustness analysis of neural networks, this was a really stress testing application for HiDiff. The execution and the analysis were expensive, but still HiDiff was able to generate significantly more output differences than fuzzing and symbolic execution. Well, so this was a very brief introduction into HiDiff. If you want to get more details, please check out our paper and our artifacts. They have been evaluated and are online available on GitHub. Thank you for your attention, and I'm happy to answer questions.
All right, Yannick, thank you for your great work and the nice presentation. Fellas, go ahead with questions for Yannick. We have 4 minutes. So in the meanwhile, I can do one warm-up question myself. Like, how do you determine that, say, an output difference is a bug and not a divergent yet correct execution state, for instance?
Yes, so for example, for regression testing, we cannot say that because there might be the divergences which are intended, like a bug fix, or unintended. So this needs a post-processing of these output differences, which we did not conduct in our experiments. Okay. But for example, if you have an exception in the new version, and then of course this is probably a bug. Yeah, and this is something also which we can detect.
All right. So we have a question from the audience, like, nice talk. How similar do the two applications need to be? Could you apply the idea to two independent implementations of an application, for instance, two compilers?
Yeah, so this in general is possible. Our goal for regression testing, when this is not, so when you have two different, when it's not two completely different implementations, so you just have some changes. If you have complete changes, you still can apply it, but for example, for these change annotations, they will be very imprecise. You probably will annotate everything as a change, and then of course this does not bring you so much benefit. So we haven't tried it on two very different implementations. It would be interesting to apply that, but it was also not the main goal of our implementation, also not the goal of in our experiments.
All right, but I think that could be some interesting line. However, we have another question, like, are there parts of code that you cannot run both fuzzer and symbolic execution at the same time, for instance, due to complex constraints?
Yeah, so in HiDiff, both components run in parallel. So if, for example, symbolic execution does not make any progress because constraint solving is too complex or whatever reason, and then still fuzzing would run. So we would still make some progress. And then maybe at some point, symbolic execution still can contribute something. And then, of course, we can combine these information. And here also, fuzzing helps, of course, for symbolic execution because we also import the inputs from fuzzing to our symbolic execution component. And this helps to guide the symbolic execution into interesting parts. And this, of course, then again helps fuzzing because then symbolic execution can maybe generate some new inputs which are difficult to achieve with fuzzing and so on. But yeah, there are parts where both components have problems to handle. And then the combination, of course, helps.
All right, thank you. Any more questions for Yannick? I was wondering if there, like, is there any chance to see this technique applicable to generic Keras model, for instance? That would be extremely cool. Because I read that you now have to basically migrate the code to Java. Is it that difficult to generalize it to, I don't know, Keras models? What's your opinion?
To be honest, I'm not so super sure how you would do it. So at the moment, we apply on Java bytecode. So what we do for the neural networks, we have an implementation which kind of converts a neural network model into a Java program, and then we can
okay. So
analyze
it's
the Java program. Yeah.
All right. I'll thank you again for your talk and the cool work. So we hand the mic over the next presenter. with like ZU from Peking University, who is going to present a paper about uncertainty, autocharacterized uncertainty in deep learning software systems to detect adversarial examples. Unmute yourself and share your screen, please.
Can you hear me now, Andrew?
Yes.
Okay. Hi, everyone. I'm Xue Zhang from Peking University. Today, I'm going to talk about a paper characterizing adversarial defects of deep learning software from the lens of uncertainty. Over the past years, we have witnessed the success of deep learning in a variety of applications, such as autonomous driving, manufacturing, and smart devices. Like traditional systems, deep learning systems also suffer from vulnerabilities. One typical representative is the adversarial example. Such errors, for example, in autonomous driving scenario, could lead to tremendous loss and severe consequences. Typically, a DL model is a function mapping an input data to a distribution or a set of labels. In this cat-dog binary classification problem, when the output distribution is 99% versus 1%, the model presents the decision cat with a very high confidence. When the output distribution is 20% versus 80%, it states that the model has seen features of dog and some certain features of cat. So it states it presents the decision dog with relatively lower confidence than the first image. The prediction confidence has been used to reflect the distance to the decision boundary, and it has been widely used to characterize the behavior of deep learning models on different inputs. Normally, we use a single well-trained model with fixed weights to help us make decisions. Unlike the deterministic execution with a fixed boundary, Bayesian framework regards the weights as random variables obeying a distribution, and therefore leading to a range of boundaries. We can do predictions on a set of models with weights sampled from the distribution. For example, if we sample 3 times from the distribution, when we feed the input image cat to the sampled models, the outputs demonstrate 3 cat with high probability values. This indicates low uncertainty toward the input image cat. When we feed the dog image to the sampled models, the outputs demonstrate 2 dogs and a cat. The higher variation degree in the outputs demonstrate higher uncertainty towards the input image. We use Monte Carlo dropout to help us estimate uncertainty measures. It is a practical method and is scalable to large models. We perform multiple forward passes for the same input. With the support of dropout, we can guide the predictions in different network structures. Uncertainty measures can be estimated based on the outputs of the ensembled models. Existing techniques, for example, the attack methods, only leverage label probability to generate adversarial inputs. Such inputs might cross the fixed boundary, but what behavior will they trigger with regard to a range of boundaries? How about the testing inputs generated by testing techniques or the benign inputs? What kind of behavior will they demonstrate? This motivates us to adopt prediction confidence and Bayesian uncertainty measures to characterize such data inputs for further study. This is an overview of our work. We intend to achieve 3 research goals. First, since there are multiple types of uncertainty metrics, we want to study their ability in differentiating adversarial inputs and benign inputs. Second, we want to characterize the data inputs generated by existing techniques and identify if there exist any uncertainty patterns. Finally, we try to generate data with uncommon patterns that are largely missed by existing techniques. About the metric study, we collect the prediction confidence based on uncertainty measures, including the probability confidence difference, Gaussian ratio, entropy, mutual information. Then we evaluate their ability in differentiating benign and adversarial examples. Here comes the first research question about the effectiveness of different uncertainty metrics. We use AURC score to measure the separation ability for each metric. The results on 3 datasets across 4 model architectures also show that prediction confidence score and the version ratio have the best performance from the perspective of deterministic execution and the Bayesian ensemble execution. Based on the numerical study result, we select the prediction confidence score and the version ratio to characterize the data inputs. They can be calculated following the formal definitions. The data for characterization are collected from multiple sources. We adopt 4 attack methods, 2 testing techniques to generate the adversarial inputs. The well-classified test data are the benign inputs. We have observed that different types of inputs have specific patterns. The results here shows that we can see from the results that benign inputs mainly have the high prediction confidence score and low version ratio. For example, the benign inputs of NIN have about 0.95 prediction confidence score and 0.05 version ratio. Intuitively, this means that the benign inputs are far from the fixed decision boundary, and the ensembled outputs are mostly consistent with small variation degree. The adversarial examples from attacks mainly have low prediction confidence score and high version ratio. Compared with the attacks, testing techniques would adopt more mutation strategies, so the generated inputs demonstrate more diverse behavior. To this end, we have characterized the data inputs generated by existing techniques and identify the common patterns they demonstrate, HL for benign inputs, LH for adversarial inputs. Naturally, we would wonder, is it possible to generate data with the remaining uncommon patterns? For example, the benign inputs with LH pattern or adversarial inputs with high prediction confidence and low version ratio, or data inputs with the other 2 LLHH patterns. We leverage the uncertainty metric to generate inputs with targeted patterns following the workflow of genetic algorithm. After the population initialization, we check if the generated data satisfy the objective of the targeted pattern. If not, we select the data with the largest fitness values to perform crossover and mutation. The test generation stops when the objective is satisfied. When generating inputs with different target patterns, we use the L infinity norm to constrain the perturbation and guarantee the validity of the generated data. The results show that data inputs with different target patterns all could be generated by our metric-guided method while preserving the validity. Finally, we evaluate the effectiveness of the generated inputs in bypassing defense mechanism. For binary classifier and mutation-based defense, our method demonstrates strong advantage. For example, the generated inputs have demonstrated about 90% defense success rate reduction towards the NIN model and ResNet 20 models. On average, compared with the data of common patterns, the generated inputs from our method reduce the defense success rate with 35%. In summary, we first perform a empirical study on the differentiating ability of different uncertainty metrics. Then we characterize the data inputs generated by existing techniques and identify the common patterns. Finally, we propose a genetic algorithm-based test generation technique to generate data with the targeted uncertainty patterns. Here are the references.
All right, thank you, Ziyu. Questions for the speakers? So if I comment myself, like you applied this technique to classifiers only so far. Are you planning on studying the uncertainty also, like for networks that perform regression tasks? If there are like similarities or differences.
I'm not sure if I understand it right. Do you mean that can we like
a network that has predicts a continuous value, like the stock market price or a steering angle of a self-driving car, not like a categorical question, a categorical output.
Okay, all right. I see your point. Yes, actually, compared with previous research work, the mainly difference from our research work is about that we use the Bayesian uncertainty measures to characterize the data inputs and generate more diverse generate the data inputs with more diverse patterns. But the thing is, it is very difficult to estimate the uncertainty measures. So we leverage the Monte Carlo dropout to help us to deal with this situation. Up to now, from my understanding, the dropout can be, the Monte Carlo dropout can be used to deal with the scenarios like we need to deal with classification problems. Because you see that we characterize the data inputs from the features of the output distribution. So it is a limitation or method because we only focus on the discrete classes.
Okay, I see. That's fine. We have like lots of questions popping up, so I think I would forward all of them to you in the offline session. We have time for one more, however, which is, can this adversary use this knowledge to create more advanced attacks that are harder to detect? For instance.
Do you mean that we are the work actually serves as a more powerful attack? Yes, but mainly our main aim is to like generate more diverse test inputs. It's only that we use a way to characterize them with the uncertainty patterns, and from the perspective of different patterns, we aim to generate more diverse test inputs. But sure, here we can see that we also aim to generate the adversarial inputs with high protein confidence score and low Bayesian ratio. Those are the uncertainty patterns that benign inputs have. So we can generate the more powerful adversarial inputs, more powerful attacks, because it is more similar to benign inputs. So the models, the deep learning system can be more confused to classify them correctly.
All right, thank you. Thank you again for the nice work. So we can hand over the mic to the next presenter, who is gonna be like Anastasia Danilova from University of Bonn, Germany. And Anastasia is going to present us this paper about one size does not fit all, a grounded theory and online survey study of developer preferences for security warning types. Please, Anastasia.
Thank you very much for the introduction. So my name is Anastasia Danilova, and I'm going to present our work today, and I would like to thank my co-authors for their contribution. So security warnings are a form of computer dialogue communication used to warn users about potential risks of their actions and security issues. And software developers can encounter security warnings while programming as well, and can become frustrated by them. However, we saw that security warnings can also increase the security of code. Gorski and colleagues showed that warnings can improve code security if they are displaced by the compiler. And Johnson et al. Found that developers do not use static analysis tools because of the poor integration into developers' workflows. And therefore, we wondered, what are developers' wishes concerning when and how they would like to be warned during the software development process? and also which types of warnings do they prefer, as there are a number of different types which could be integrated into the IDE. So our study consists of two parts. First, we conducted a qualitative analysis with 14 professional software developers and 12 computer science students, as well as a focus group with 7 academic researchers. And for the evaluation, we used grounded theory by Sharmas with theoretical sampling to get a broad overview of the problem space, as well as we followed up this qualitative work with 50 developers to test the developed themes and explanatory theory. To decide which types of warnings to use, related works on security bugs was reviewed and the findings were discussed with colleagues from the field of computer science. And I will now show you the different warning types we showed our participants in our study. The first warning type is a common warning marker used by many IDEs, which means underlining the issue in the code and showing a left warning marker, and at the side you see like an icon, and we added the variation of this with a blue as a new color for security warnings, and we added the log icon as a warning marker to stress the security. And next we have compiler warnings, meaning warnings which are displayed in the compiler output. Further, we illustrated a warning view inspired by static analyzer plugins like PMD or FindBugs. And also it's possible to have a warning view solely for security issues, which we call the security view. We also included pop-up warnings because they are also used for end-user warnings. And we included 2 further pop-up warnings variants, which only appear when code is committed. So the first one appears on committing and asks whether the developer would still like to commit or go back to the issue. And the second one was added as part of the grounded theory approach based on the feedbacks of our participants. And it's a pop-up warning on committing, where you also have the option to delegate a ticket to a colleague. And now let's discuss our results. Our theory grounded in our data suggests that context is the key. Developers' stated preferences are based on coding purpose, developers' characteristics, team and organization context. And we found that customizability for security warnings can be a desired feature. All of our participants had experience with the standard yellow warning marker, and however, some participants reported that they tend to ignore them. The yellow markers allow code to compile and therefore could be regarded as less important. And the yellow warning marker is also difficult to be found in a large code base. Also, one participant stated that it's not enough space to display the warning message properly. Others, however, favored the marker because they are familiar with it, and they also liked the security color, like the blue security color marker, indicating that it's a security issue. For the warning and security views, most IDEs already allow plugins to add sub-windows to the IDE, and they have the option to switch to dedicated views with a set of windows for a specific purpose, such as debugging or security testing. However, a number of participants found that the user interface of IDEs is already overloaded. Also, some participants stated that they needed to familiarize themselves before working with plugins. Others, however, were already familiar with views and therefore favored them. So let's discuss compiler warnings. Our participants had mixed feelings about compiler warnings. Some participants found that compiler warnings could be easily overlooked because compilers can produce a lot of input, which can hide the warnings. By contrast, other participants had positive feelings about compiler warnings and even stated that they could be one of their most favorite approach. The majority of our participants did not like the idea of pop-ups because they are distracting and annoying and would disrupt the programming workflow. However, some participants with more programming experience, they had the negative opinions, but there were also participants with less programming experience, like 1 to 4 years, which favored pop-ups. And some students said that in very important cases, distracting pop-ups could be useful to catch the attention of the programmer. Additionally, some experienced participants admitted that pop-ups could be useful in certain situations, such as when a developer initiates an action like committing code. So the vast majority of our participants found warnings on committing to be one of the best because it does not interrupt the coding process. However, it's most visible and noticeable. For the question which type was rated the most favored, multiple answers were possible, and we know what no type was the clear winner. And however, we found a correlation between fitting the workflow and the positive opinion on the warning types. So it's very likely that configuring the warning could be beneficial. The next question was when to display warnings. And also we see here that a lot of participants would like to be warned before committing, before running the code, or on demand. So therefore our takeaways are that warnings were regarded as a good way to raise security awareness for developers. However, we had a lot of different preferences in when to be warned and how to display the warnings in the software development process. And we found that the developer's context needs to be considered. So what is the company of the developers? How is the team structured? What is the coding purpose of the code the developer is programming? Is the developer only programming a small snippet to get something done, or is it a coding snippet for a important software which will be used after release as well? And also the characteristics of the developers need to be considered. So there are developers who are more security aware because maybe they are working in a company which is security aware. So therefore companies implement different policies and regulations, and also the security focus of the companies is different. And team colleagues are also an important factor to consider, because some participants noted that they would like to delegate their tickets to colleagues, and others said that if they would delegate the ticket, the issue would be lost and nobody would deal with it.
All right. Can you quickly
So
wrap up?
our recommendation are consider the context, warnings visualization should be configurable, and warnings are a good thing to consider.
Right, indeed. Thank you, Anastasia. You have a few questions, like the modalities you have evaluated are general and not specific to security warnings. Do your results generalize beyond security warnings? And if not, why?
I would say that security warnings, so our results might generalize to general warnings, but we need to be cautious because security is tricky. So I would say that security is more important than other bugs. Like so security needs to be considered on its own, I think, because other bugs can, if we have warnings for each little bug, it could be that the developers get annoyed and feels like switching off the warnings completely. So
Right.
therefore, it's not. It should be considered, I would say.
Okay.
So the warning
Makes sense.
type should be considered.
All right. Another person asks, you have focused on displaying warnings, but developers also want and need to act upon them, like solving, marking them as irrelevant. Do you expect differences because of this?
It's a good point, I think. So I think it's necessary to consider developers ignoring, like switching off the warnings or marking them as solved. So I would say that it needs to be considered.
All right. I got like 2 more questions. Let's try to be brief. How did you check that participants encountered the warnings in a typical development context in which they would work? I'm not sure.
This is a difficult question. Yeah, it's really difficult to test the warnings in a real life application because developers work with different IDEs. Therefore, we only asked them about their opinions, and we did not test it like in real life.
Right.
Right now, it's a bit too difficult. Maybe we can work with Eclipse, for example, in the future and test it in a more in a more controlled environment.
All right, all right. I thank you again, Anastasia, for your nice work, and I ask Kun to be ready to set up his screen. Our next presenter is Kun Excout from Leuven, Belgium. I was going to present our a near paper about threat modeling from infancy to maturity. Please, Kun.
Okay, hi. So thanks for the introduction. This is joint work between the Distrinet Research Group at KU Leuven and Torion, which is a company specializing in threat modeling and training. So first, briefly, what is threat modeling? One of the cleanest definitions and the most succinct definitions was given by Alyssa Miller in the YouTube talk listed on the slide. And she says that threat modeling is about identifying the likely threats to a system to inform the design of security countermeasures. To concretize that a bit, threat modeling nowadays is mainly driven by answering the 4 questions given by Adam Shostak in his book, namely, what are we building? What can go wrong? What are we going to do about it? And did we do a good enough job? Now, in practice, a typical threat modeling process at Torion looks like this. So first, they have a kickoff meeting, and then there's a modeling session where people work together in a room to create an overview of the system on a whiteboard. And this can be very chaotic, and an analyst will spend some time to consolidate and finalize the results. Then in a follow-up session, the actual model of the system is used to find security threats using techniques such as STRIDE. And again, an expert needs to consolidate the elicited threats, rank them, and propose some mitigations. And here, the knowledge of the expert is really crucial. Then finally, there are reports created and a review meeting is held, and the people involved agree on where to go next. Now, this all seems to work fine, but the position that we take in our paper is that threat modeling at this point is still, as an engineering discipline, at a very low level of maturity, both in terms of research, tool support, and in practice. So it's a bit ad hoc, driven by expert knowledge, but there's not a lot of scientific research about it. So what we've done in our paper is outline 5 maturity levels for threat modeling and identify the research challenges that are needed to move from one level to another. So as I've said before, we're currently at the first level, an ad hoc level. And the second maturity level still relies heavily on intuition and expert knowledge, but the activity itself becomes more repeatable. So this requires a reference model that can be used to capture and exchange threat modeling information artifacts. And this could be used, for instance, when you're repeating the process at a later time, but also to share examples and educate others. In the third maturity level, the importance of the individual expertise should be reduced because relying on experts doesn't scale well. And what is needed here are better ways to track the end result, but also the assumptions and the decisions that are made along the way. And on top of that, it becomes important to not rely on the knowledge of the expert, but to create security knowledge bases and use them. For the fourth maturity level, we need metrics to assess the quality of a threat model and the process that was used to create it. And these metrics should help to manage the process and make predictions about cost-benefit trade-offs. for example, to assess whether some threat model still corresponds to reality. And then finally, the optimized version of threat modeling at level 5 uses these metrics from the previous level to steer the process in a continuous fashion, leading to dynamic and self-adaptive threat modeling. For example, when the risk for a threat increases, a countermeasure may be automatically deployed or strengthened. So in summary, we believe that threat modeling is a very important activity, but currently at a low level of maturity. And to improve on that, researchers and practitioners should invest in creating better models, tools, and knowledge bases. And our roadmap is a first step in this direction. Thank you.
Thank you, Kun. Any questions from the audience? So you discussed about threats, but what about the mitigation strategies?
The mitigation strategies are typically quite well known. So once you know what can go wrong, it's not that hard to find out what you can do about it. Okay. But indeed, the both should be coupled.
All right, we got another question from those, which is really interesting, which is considering that threats may change over time, new vulnerabilities, new attackers, new patterns, etc. Why and how could threat modelings be ever repeatable?
Yeah, so that's one of the problems that our industry partner highlighted. If this exercise has to be repeated, then the whole process that I sketched has to be done from the beginning again. So one of the things in our maturity model would be to capture this in a way that you can have targeted changes or updates without doing the whole exercise again.
All right, I thank you for the nice presentation. So this is pretty much all for this session. We have one presenter who is unfortunately missing. So I'll let the virtualization team to decide whether they want to play the video or like continue and move on to the next session.
Hello, my name is Gianluca Scoccia and I'm a postdoc researcher at the University of L'Aquila, and I'm going to present our work, Hey, My Data Are Mine, Active Data to Empower the User. Nowadays, we live in a society where there is a trend going on in which we are increasingly interacting and cooperating with digital systems like mobile devices, smartwatches, autonomous cars, service robots, and so on. However, in order to exploit the benefits and the opportunities of these digital systems, we are obliged to share our personal data with them. And the problem is that once on the network, we lose control of our personal data, and this data is in the hands of the system producers and no longer in control of the original owner. This problem arises from the fact that data has always been considered as passive entities, and the logic that controls the life cycle of data is decoupled from data themselves. Hence, we propose to drastically change the nature of data from passive to active. And an active data object, in our vision, is a software module that wraps, encapsulates, and protects personal data. How do we imagine this active data module? Well, we imagine that in addition to the personal data, there are a series of additional components required to protect the data. These are a monitor and enforcer, and a lifecycle status, that is a number of variables to keep trace of the lifecycle of the active data, like, for instance, the number of existing copies. Then there are some privacy rules that are defined by the owner of the personal data and are evaluated according to the information available in the lifecycle status. And then there are two different kinds of operations that are accessible through APIs. These are I/O operations that provide mediated access to the personal data, and the internal operations that actually operate on the data. The monitor and enforcer actually verifies that the accesses to the APIs comply with the privacy rules and only allows those to comply to go through. And we imagine that all the active data modules are executed inside the secure execution environments that can be software-defined or hardware-defined. However, with a single active data module, there is still a limited control that we can exert on the personal data. Hence, we imagine that all the active data modules are connected together into an active data network to control and manage the life cycle of all the copies. In this network, the owner node is the active data network manager. It keeps trace of its own active data network and enables the update of privacy policies. And on this network, consensus protocols are put into action to ensure that accesses to the active data comply to the privacy rules. This concludes my presentation, and if you're interested in our project, we are available for questions or comments on the following email addresses. Thank you for your attention. Hello.
All right, time to conclude this session and hand over the mic to the next session chair, my colleague Pojan. Please, the stage is yours.
Okay, hello everybody. I'm so excited to start this session on deep learning testing and debugging. As all of you know, this is basically a session presenting work from software engineering community, contributing how to fix bugs and other adversarial issues in machine learning systems. So in this session, we have 6 presentations, which include 4 technical papers and 2 demos. And more importantly, out of these 4 technical papers, 3 of them are distinguished. So I'm really looking forward to these exciting talks. The first presentation is the sector input validation for deep learning applications by cross-cutting layer dissection. And this work is going to be presented by Huang Wang. Huang?
Excuse me.
Hello.
Excuse me. Sorry for the interruption, but we are going to have a break time for 5 minutes. Yeah, sorry for the late interruption. Yeah.
Okay, sure. Do you want me to introduce the session again or not?
We are just going to start it after 5 minutes without the session introduction. Yeah, sorry for the interruption.
No worries.
honor to give a speech here. I'm from Nanjing University in China. My talk today is about dissector, an input validation technique for deep learning applications by crossing layer dissection. As we all know, deep learning applications are quite popular recently. However, due to their imperfect accuracy in practice, their wrong predictions in practice may cause some runtime reliability issues or even lead to some tremendous disasters in our life. We ascribe this to its key differences from traditional applications. For a traditional application, there is a clear specification for its logics, so it could be very easy to identify some wrong behaviors. However, for a deep learning application, its logic is normally generalized from large-scale samples, and there is no clear specification. Therefore, it is hard to practically examine or identify some wrong behaviors at its testing and deployment. Our focus today is how can we assure its reliability specifically. We consider a fault-tolerant way to do that. If any unexpected input is fed during the deep learning applications, we consider the deployed application with its own handling capability. For an input within its capability, we expect the application to work well. Otherwise, we can isolate such beyond input to avoid some unexpected wrong decisions later. Therefore, in a fault-tolerant way, our problem can now be transferred to a typical input validation problem. To be specific, for the kernel deep learning model in a deployed application, it has its own capability scope. Input within such scope usually contribute to high accuracy. Inputs beyond such scope may lead to dramatically decreased accuracy. Our real problem here is how can we distinguish such within and beyond inputs well at runtime. We actually expecting our distinguishment to be both effective and efficient. Concerning some existing practice, there are some work targets on the similar input validation questions. Some work targets on OOD identifications and chose to identify them by natural confidence scores. Such treatment is extremely efficient but lacks sufficient effectiveness. Some techniques target on adversarial or corner case identification. This treatment is very good, effective, but tend to be not efficient enough. We try to address our problem and balance its effectiveness and efficiency at the same time. Therefore, we are actually seeking for a quite lightweight and effective heuristic idea. Our idea here on identifying the within input is such input corresponding to an increasingly consistent prediction process. To better understand our idea, we now give a daily human recognition scene for illustration. There, in the slide, there is a guy walking closer and closer. We are gradually guessing who is this coming person. Here are two different recognitions. Although they both get the final B result in our guess, they actually differ from each other. The above one is more fluctuated and we can be easily confused during the poll process. The below one is much more smooth and eventually consistent to each other. Therefore, we naturally consider the below one to be more trustable in our daily thing. Now, this daily thing naturally maps our idea for identify the within input for deep learning application. Such a trustable recognition actually echoed the increasingly consistent for within input in our heuristic idea. Now we now map it to the deep learning prediction thing. Such two things share a similar step-by-step style. They both target on giving the final prediction with guesses gradually. This mapping is quite straightforward. And then we move to the deep learning thing. Such input picture is now predicted along the deep learning model and gets its final result as a stop sign. Here are two different guess profiles. The above one keeps inconsistent and the below one is increasingly consistent. The below one actually suiting our heuristic idea very much. We would similarly consider it to be more trustable. In our later study, we actually observed over 95% high accurate samples share such an increasingly consistent guess profile. Therefore, our dissector approach actually has two tasks. First, given given an input sample, how can we obtain its gas profile? And second, based on such profile, how can we measure its gas consistency? Now for the first task. In a gas profile, its final gas, in this example, is a stop sign. It's actually straightforward and given as a prediction result. But if intermediate gases are not easy to obtain, it may need some preparations. We chose to dissect the deployed deep learning model into a list of partial models for each layer. Each partial model is a submodel that links the formal deep learning model until this layer with the newly trained LR structure. After such preparation offline, this trained submodel can be used for any sample to get its intermediate gases. And now we move to the task 2. With such preparation of gas profile, how can we measure its gas consistency now? We consider to measure each gas uniqueness and combine them together to get a final score of the gas consistency. For each intermediate gas in the profile, we measure its uniqueness in this way. There are actually 2 cases. For the first case, if this specific intermediate gas is equals to the final gas, we measure the range between it and the second highest level. The larger range, the better uniqueness. Otherwise, we measure their range between each other. The larger range, the worse uniqueness. Generally, such measured uniqueness represents how much this intermediate gas supports the final prediction. And then we combine them together, considering a growing weight for modeling increasingly consistent property. The final score is normalized between 0 and 1. The closer to 1, the more increasingly consistent this profile is, and the more likely it is to be a within input. Until now, our approach is able to measure the gas profile for any input sample at runtime and gives its score on within beyond distinguishment. We experimentally evaluate our approach on several subjects and compare it with 2 existing techniques concerning both its effectiveness and efficiency. For effectiveness, such results show that upon our AUC measurement for effectiveness, our dissector can be quite effective by obtaining all nice AUC superiority ranges and landslide victory over existing approaches. And now, for efficiency. Our dissector is quite efficient. Its key input validation part only takes 3 to 4 milliseconds per sample, while existing approaches take several 10 or hundreds times of large overhead. Even for some complex subjects like ImageNet, dissector still only needs to 5.8 milliseconds for validation, while both existing approaches fail to apply. Despite its effectiveness and efficiency, dissector can also be used in many other fields. In our study, such input distinguishment can also be applied in many different areas, such as identify adversarial inputs and improve actual accuracy in use through beyond input isolation. Moreover, using dissector as a wrapper can help us to tolerate some imperfect models and give us an opportunity to compare different deep learning models and even some different deployment scenarios in a quantitative way. And at last, we conclude our presentation today. First, we talk about the reliability issues that deep learning applications have and proposed an input validation way to address them. We gave our scope hypothesis and based on it, introduced how we inspect such a gas profile and measure its gas consistency. Then we elaborate on dissector's 2 tasks and evaluate its performance, and we finally discussed about its usages. Thank you. That's all for my today's talk.
Thank you. It was a great presentation, Huyang. So we have a couple of questions here. Fitash is asking, hi, thank you for the amazing talk. Can we use this to retrain the model, as it is possible to extend this approach to regression tasks? So basically 2 questions. Can we use this to retrain a model, and is it possible to apply for regression?
Yes, the 2 questions are actually very great. And for the first one, can we use our dissector to retrain the model? My answer is yes. Actually, using our detect can be quite different. You can use it to identify the within and beyond input. When you are trying to retraining the model, you may try to expand existing scope by retraining the model within more beyond input, or you can also try to strengthen the original scope by adding more by isolating more beyond inputs. These are actually two different retraining directions. And for the second question, is this possible to extend our approach to the regression task? Is that right?
Yes, but unfortunately, we have to move on to the next talk.
Oh, sorry. Thank you.
I'm so sorry about that. So next talk is about white box fairness testing through adversarial sampling. And the work is going to be presented by Taxin Zhang. Taxin, if you go ahead.
Okay, wait a second. Hello, everyone. Thank you for coming today. Oh, sorry. Hello, everyone. Thank you for coming today. My name is Peixin Zhang, a PhD candidate from Zhejiang University. I'm glad to be here to present our paper, White Box Fairness Testing through Adversary Sampling. The reason why we study fairness is that in modern society, discriminations such as racism and sexism are still common to see and even become more intense nowadays, which leads to there are often societal bias in the collected data. Thus, deep learning models learned from historical data might introduce discrimination unintentionally. Then, with the spread of deep neural network, its fairness raises more attention among public, especially the minority. Therefore, governments, including US, Chinese, and the European Commission, all list fairness as one of the most important principles for trustworthy AI in their AI development guidelines. Actually, there are multiple definitions of fairness in AI and the software engineering community, such as demographic parity and equal opportunity. In this work, we only focus on solving the problem of individual fairness, which is defined as a model must predict the same labels for all feature vectors that are the same except for those protected attributes, such as gender and race. And we mark those valid instances which violated the given definition as individual discriminatory instance. For example, for a toxic classifier, it should give the same predictions on the given examples where gender is the protected attribute. Now, the problem of fairness testing is how can we effectively and efficiently generate individual discriminatory instances for a given model. There are three existing individual fairness testing methods. They either relies on the randomness or combines model explanation and symbolic execution, which limit their effectiveness or efficiency. Besides, although they are suitable for all the machine learning algorithms, they perform much worse in deep learning models according to their experiment. Therefore, we try to design a better algorithm specifically for deep learning models. According to the definition, individual fairness can be seen as a specific form of robustness, which maintains the prediction when protected attributes changed. Thus, inspired by the adversary attack, we try to perturb X and X apostrophe, which only differ on the protected attributes at the same time to push them towards the decision boundary. And if only one of them across the decision boundary, we are successfully obtain the individual discriminatory instance. Here is the overview of our algorithm ADF. We divide it into two stages. First, global generation aims to increase the diversity in the generated individual discriminatory instance. And then, based on the robustness of deep neural network, local generation tries to obtain more and more individual discriminatory instance by searching the neighbors on the identified ones. Although both phrases need to calculate the gradient, they utilize it in a different way. Next, we will detail these two phrases. In global generation, there are three challenges needed to address. The first one is how to improve the diversity of the testing data. We provide a direct way by clustering the data and popping the seed in a round-robin fashion. And second, how do we perturb the data? Inspired by fast gradient sign method in adversary attack, we select the perturbed attributes with the same sign of gradients and utilize the sign as the perturbation direction. And last, how do we keep the generated test case real? Since the experimented datasets are quite simple, we only clip each attribute within its domain. Compared with global generation, local generation is much easier. Its first problem is how do we choose the attribute to perturb? Since gradient shows the impact on output, we select perturbed attribute based on the absolute value of gradients. And the same with global generation, we clip each attribute within its domain to make data valid. Compared to existing approaches, our algorithm satisfies all the listed three criteria. First, ADF is guided by gradient, which accelerates the discovery of more individual discriminatory instances. Second, our algorithm is input specific, which improves the diversity of generated test cases. Last, ADF is lightweight, which makes it more scalable. We evaluate ADF with 6 benchmarks on 3 popular tabular datasets. Since the datasets are quite simple with no more than 20 features, we only use a 6-layer fully connected neural network, and we aim to answer 3 research questions about the effectiveness and efficiency of ADF, and the usefulness of individual discriminatory instances identified by ADF. First, we conduct effectiveness evaluation phrase by phrase for a fair comparison. Both in global and local generation, we try to generate 1,000 test cases and check whether they are individual discriminatory instances. It is evident that our algorithm ADF is more effective than state-of-the-art methods. Next, the table lists the time each method takes to successfully generate 1,000 individual discriminatory instances. It is clear that our algorithm ADF is more efficient. And last, we try to improve model fairness by retraining with data augmentation. The table gives the ratio of individual discriminatory instances estimated by the law of large number. It can be observed that retraining with the individual discriminatory instance can significantly improve the model fairness, and ADF achieves better fairness improvement. In conclusion, inspired by adversary sampling, we propose a lightweight algorithm to effectively and efficiently generate individual discriminatory instances, and in the future, we try to expand it to text and image domain. That's all. Thank you.
Thank you very much for a great presentation. I really enjoyed it. So let's, we have a few minutes for questions and answers. We have a couple of them already. Can we remove the protected labels during model training? Will this be helpful for creating more fair model?
No, you mean just, that's a good question. You mean just move the protected attributes and training the model without the protected attributes?
Yes, I think so, yeah.
It's a way, but for some attributes like gender and race, it's obvious it's obvious it's protected attributes, but in some data sets, there may be some more how to say, more hidden the attributes may be more hidden. For example, maybe the name. Can you do you the name because the name for boys and girls is may be different, but we cannot list them all to distinguish which is the protected attributes.
Right, that makes sense. Another question, thanks for the great talk. Is it possible to extend the approach to other domains like text and images?
It is possible to expand it to text. We just do it right now, and it's difficult to do this in image domain because, for example, face recognition, you need to change the color of a person, and or the nose, the type of nose of a person. But I think it can be addressed by like deepfake, which one? Deepfake, and another GAN methods.
Right. Yeah, that's a fair answer. Another question. Thanks. How can we know whether a label is protected in a data set?
Pardon?
They're asking, how can we know whether a label is protected in a particular data set that you have? So it's more like setting.
The ground truth label.
Yep.
It is we label the generated individual discriminator instance using the idea of majority voting from decisions of multiple models, and we try to get the multiple models by some methods like model mutation.
Yeah, that makes sense. Thank you very much for all the answers. We have to move on to the next demo paper. Is called FeatureNet Diversity-Driven Generation of Deep Learning Models, and this is going to be live streamed by the team, by Salah Amizi.
Hello everyone, my name is Salah and I am working at SNT University of Luxembourg with my supervisors Maxime, Mike and Yves, where I've been studying how to generate a lot of diverse architectures. Deep learning testing have become more and more popular and requires tools to run large-scale experiments. Our tool relies on a new representation of neural networks made of cells. Each cell component handles a specific category of operations like convolution and pooling. Cells are organized within blocks that allow the network to branch, parallelize, and merge. FeatureNet parses the blocks and cells into a full working neural network using TensorFlow and Keras. It also fixes its inconsistencies. It selects architecture that maximize the diversity of their components in order to cover a wide spectrum of behaviors. The models are then trained and tested. The most performant models are then used to run your custom experiments. It can be computation of neural coverage, generalization, studying the explainability or the robustness of the model. We provide our tool in different flavors. First, using a user interface, where you can define different parameters of sampling and the dataset. The tool will build the feature model, parse it, study the configurations, and then it will run the training and the evaluation. Once the tasks are completed, you can see the results of the generated model, first with the summary, and more specifically, you can browse all the models and architecture that have been generated and the performance metrics that have been computed. In addition, you can also either see the graph of the model or download the architectures immediately to use them for your custom experiments. Finally, the dashboard provides you an overview of all the architecture on different metrics that have been computed. Our tool can also be used within your pipeline using a command line interface, where you can provide the parameters of the tool and then run all your experiments. Finally, we also provide an API that can be integrated, so you can extend the tool with your own experiment and code. Here, for instance, we are running an experiment to compute the weights and the correlation between the layers. As you can see, you can just plug in your hooks or your experiment and then run the TensorFlow code.
Hi, I'm Ru. I will be presenting.
Yes, we need to move on to the next demo paper again, Eval BNN, a toolbox for evaluating deep neural network models.
Hello, everyone. My name is Yongqiang Tian. I'm a PhD student from the Hong Kong University of Science and Technology. Today, I'm going to present our work, EvalDN. It's a toolbox for model evaluation of deep learning systems. It's a joint work by several universities. Currently, if you want to evaluate deep learning models from multiple perspectives, you need to do the following things. First, you need to learn the API of deep learning frameworks. Second, you need to write tens of lines code for each evaluation matrix. After that, you need to spend some time to ensure the correctness and improve the evaluation efficiency. Such a process is time-consuming and error-prone. To help the user in such a scenario, we design a toolbox called EvalDN. With this toolbox, users only need to prepare their dataset and their model and feed them into the EvalDN. And EvalDN will generate reports. EvalDN supports multiple evaluation metrics, including accuracy, robustness, neural coverage. It also supports multiple frameworks, such as TensorFlow, PyTorch, MXNet, and Keras. It also provides a set of unified interface so the user can easily add a new framework and matrix. EvalDN will bring the following benefits. First, you don't need to learn the API of deep learning frameworks. Second, you can finish the evaluation in less than 10 lines of code. Third, we use unit tests to guarantee correctness, and we use parallel computing to improve the efficiency of the evaluations. Moreover, you can easily add your own customized framework and evaluation matrix. We believe this will help the developer and researchers who want to propose new framework and evaluation matrix. With EvalDN, we prepare a reproducible multi-dimensional benchmark. It contains around 80 models from 4 model zones, and the evaluation contains accuracy, neural coverage, and robustness. Here is some examples of our benchmark. We hope it can help the future studies. Thanks for watching our video. You can go our website to find more details. Please contact us if you have any questions.
Awesome. Yeah, thank you very much. So the next paper presentation is going to be Taxonomy of Real Faults in Deep Learning Systems, and the work is going to be presented by Nargis Ambatova. Nargis, go ahead, thanks.
Yes. Thank you for the introduction. So my name is Nargis, and today I'm going to present our paper on taxonomy of real faults in deep learning systems. As deep learning or shortly DL solutions are integrated into an increasing number of safety-critical applications, ensuring their robustness and understanding the reasons behind failures is very important. We define as a failure the inability of a DL component to exhibit behavior that was expected in accordance with the performance requirements. On the example here, you can see on the right an autonomous car that fails to follow the truck as it does on the left and goes into the lake. It's clearly a failure for an autonomous vehicle. Usually, in traditional software, a root cause of its failure is a fault that occurred during the development of an application. However, the notion of fault in deep learning is slightly more complex, as the behavior of a DL component is not exclusively programmed in its source code, but it also depends on a number of other aspects, such as selected model architecture or the way the component was trained. As a consequence, in order to be able to build efficient testing techniques tailored specifically for DL systems, it's important to have a good understanding and thorough classification of types of real faults that occur during DL development. And this served as a main motivation for this work. So we have started by identifying the most popular frameworks that provide developers with building blocks to implement their models. And this happened to be PyTorch, Keras, and TensorFlow. Then, to collect the information at faults that occur during development with these frameworks, we refer to GitHub and Stack Overflow, which are two large platforms that are massively used for issue reporting. In total, we were able to compile a dataset of more than 6,000 issues. To analyze the data collected from GitHub and Stack Overflow, we followed a manual open coding procedure. Each document was assigned to two evaluators that independently labeled the documents by assigning a short descriptive tag. Here you can see some of the examples. The labeling process was supported by a web application that one of the authors implemented specifically to facilitate the labeling and to solve arising conflicts. When a conflict arose, it automatically assigned the document to additional evaluator. The labeling was organized into 6 rounds, and each of them was followed by a meeting among all of the authors where we discussed the progress and solved the remaining conflicts. After the 4th round, we have started to build the initial taxonomy, and we have decided to finish the labeling once a new labeling round did not result in the addition of any new inner categories. Overall, we tagged more than 1,000 documents at this stage. While Stack Overflow and GitHub are rich sources of information, the nature of these platforms limit issues reported there to mostly code-specific problems. And in order to get a fuller picture, we decided to perform interviews with researchers and industrial practitioners that are involved in DL development. We have recruited 20 participants from personal contacts, top answerers on Stack Overflow, and a large freelancing platform called Upwork. All of the participants were interviewed by 2 of the authors, with one of them always being a main interviewer and another one asking additional questions. All of the interviews were semi-structured, which means that we first started with a very general question on the topic, and then, based on the answers we got, we proceeded with more specific questions. We have recorded and transcribed all of the interviews given the consent of the participants. And then we analyzed the context of the transcribed interviews by following manual open coding. As a result, we have complemented our taxonomy by the addition of 2 more inner nodes and 27 unique types of real faults. Here you can see our final taxonomy, which is organized into 5 top-level categories, with 3 of them further divided into subcategories. In the brackets, you can see 2 numbers separated by a plus sign. The first number indicates the contribution to the taxonomy from GitHub and Stack Overflow, and the second one from the interviews. Let's now focus on 2 of the categories that are the most specific to deep learning. The first one, the model category, features types of faults that are related to the model architecture. One example could be when a developer doesn't add the dropout layers to the architecture, and it results in worse generalization and, as a consequence, in a drop of accuracy. The next category is the training category, which is the largest in the taxonomy, and it covers various types of faults that are related to the training phase. An example could be adopting a learning rate which is not optimal to train the network at hand, or using an unbalanced training data set that would cause the network to be biased towards the class that is better represented. To ensure that our final taxonomy is comprehensive and actually representative of real DL faults, we decided to validate it through a survey that involved a new set of 21 practitioners that were recruited through the same sources as for the interviews. In the survey, we have presented our participants with descriptions and examples of the categories or larger subcategories of the taxonomy, and we asked whether the participants experienced such type of faults, how severe they were, and how much effort it took for them to solve these problems. We also asked to report any types of faults that they experienced but that were not covered by the survey. As a result of the validation of the categories of our taxonomy were confirmed with an average confirmation rate of 66%. It showed that the taxonomy is actually representative of real faults that happen during developing DL systems. Additionally, the survey did not reveal any novel types of faults, which outlines that our taxonomy is actually comprehensive. So to conclude, as a result of this work, we have obtained a taxonomy of real faults in deep learning systems, which was validated by a survey with 21 practitioners from the field. So such a taxonomy could be used as a reference for researchers or as a checklist for DL testers. It could also aid developers to avoid common pitfalls. In our future work, we plan to use this taxonomy to improve existing testing techniques and, for example, as a source for the definition of novel mutation operators. If you're interested in our work, here is the links to the replication package and to the websites of our groups. Thank you for your attention.
Great presentation. Thank you very much. It was very clear. So we have few minutes for questions and answer. For the audience, I would suggest please post your questions here so I can ask the presenter. So I have myself a question, Nargis, related to the verification of comprehensiveness of this taxonomy, right? As far as I understood, you reach out to the same people that you basically interviewed, as far as I understood, or maybe I'm wrong about that. Could you clarify on that?
No, we actually, for the validation, for the survey, we have recruited a totally new set of participants. So for the interview, we used 20 participants, and for the validation, we used a totally different set of 21 participants, but we recruited them from the same sources.
What do you mean by same sources here?
So personal contacts, top answers from Stack Overflow, and a freelancing platform called Upwork.
Okay, great. So we have a new question here. Should problems like improper hyperparameters be considered as faults per se? How close are these kind of faults to traditional software faults? That's a very good question.
So, yes, we consider insufficient tuning of hyperparameters as a fault in this case because it leads to the underperformance of the DL system. And these are not quite compared to traditional software faults because in traditional software, the faults are mostly in the source code, while in DL, it happens also to be the hyperparameters or structure of the model. So.
Yeah, great. We have another question, nice work. In your opinion, what could make the faults you identify in DL systems more difficult to predict or avoid?
Okay. There is an addition. Oh, no, sorry. Yeah. So sometimes it's quite difficult to predict such failures because the nature and the sources of possible errors are quite different from the traditional software. And as I have mentioned before, it can come from the hyperparameters. It often comes from the training data. As you can see in our taxonomy, the training phase is actually the largest part of the taxonomy. So yeah, sometimes it can be quite difficult to predict it. But for example, our taxonomy can be used as a guidance to be able to avoid such types of failures while testing, checking, for example, if the training data is balanced enough, if all the needed steps like pre-processing of the data were done correctly. So by using the taxonomy, you could actually try to avoid some common mistakes that we were able to identify.
That's great. Thanks, Nargis, again for your presentation. We are moving on to the next talk. The work is an empirical study on program failures of deep learning jobs, and the paper is going to be presented by Ru Zhang. Ru, please.
Yes. Hi, I'm Ru. I will be presenting our work in empirical study on program failures of deep learning jobs. This is a joint work with Wencong from Alibaba, Hongyu from Newcastle, and Yu Haoxiang Mao from Microsoft. To help data scientists train and test their deep learning models, enterprises build deep learning platforms, allow developers to submit and execute their deep learning programs. Philly is a similar deep learning platform internally used in Microsoft, built with widely used open source technologies and typical computing hardware. Here is an overview of the job lifecycle. Developers first upload their code script and data, then specify the job configuration such as the Docker image, number of designed GPUs, processors, make Python code files. Once that job is chosen by scheduler, Philly instantiates Docker containers to execute the launching shell script and later run the main Python code file. The job will fail if a Python exception or shell error code is thrown. The job will enter one of these three terminal status: success, killed, or failed. Every day, thousands of deep learning jobs are submitted to Philly. However, we found that a noticeable percentage of these jobs throw a runtime exception due to code or script defects and failed to complete. For example, this job had been running for 40 hours on 4 NVIDIA Tesla P100 GPUs for training, but then triggered an exception due to a wrong path configuration of test file. Therefore, reducing job failures is very important for saving precious resources, improving developer productivity, and creating business values. We propose one of the first empirical studies on program failures of deep learning jobs. To investigate failure classification, we choose 4,960 failed jobs caused by developers' code script defects. We call this the full sample set. To further understand the root causes and fixes, we selected 400 out of the total failed jobs and performed a detailed analysis of them. We call this the small sample set. And it's the failure classification overview. The figure illustrates the failure distribution across the 4 dimensions. One, execution environment, such as the file or directory used in deep learning program cannot be found. 2, deep learning specific, including GPU out of memory, tensor mismatch, and so on. 3, general code error, which means the common errors we met while using Python programming, including illegal argument, type mismatch, and key not found, and so on. 4, data. It consists of corrupted data and unexpected encoding. Deep learning specific failures are divided into 5 categories: GPU and CPU out of memory, framework API misuse, tensor mismatch, and loss none. Here is an example of GPU out of memory failure, the largest category in this dimension. The developer constructs a sequential model with a LSTM as the core layer. The input will be fed to the model in groups of data items called batches. If the batch size is too large or the model is too sophisticated due to the overlong LSTM layer, the job will consume much more GPU memory than the capacity and crash. The fix is to reduce the batch size, the max context length, or both of them, while keeping the model learning performance acceptable. The second largest category is framework API misuse. Here is an example caused by framework evolution. The developer may have thought that the latest version of Keras would be compatible with TensorFlow version 1.3. However, Keras upgrades its softmax implementation and requires TensorFlow version 1.5 or higher. The fix is to downgrade Keras to a compatible version. Here summarize the findings. 13.5 of the total failures are deep learning specific. They are mainly caused by inappropriate model parameters, structures, and framework API misunderstanding. The developers need to proactively choose the suitable model configuration and deeply understand the complex assumptions made by framework library APIs. Based on our finding, we further suggest the following possible research topics. First, memory estimation for deep learning model, which could avoid the GPU out-of-memory crash during the program execution. Second, deep learning specific static code analysis, which could help reduce tensor mismatch or other failures. API evolution analysis, API misuse detection, and dependency analysis could also be useful. Execution environment-related failures occur in the interaction with the platform rather than in the execution of code logic, accounting for nearly half of the total failures. Root cause is the model execution environment provided by platform is rather different to that for local development. Here shows an example of pass-not-found failure. The developer first used training file to train the model, then evaluate the model with the eval file. But she forgot to replace the hard-coded local file passes with the real ones on the distributed storage before job submission. The fix has two parts. First, all the passes are parameterized instead of hard-coded strings and are read from the configuration file. Second, the passes used in no matter which stage, such as the eval file variable, are validated as early as possible. Execution environment-related failures are mostly due to the unawareness of the environmental differences between local and platform. Developers need to fully understand the environmental gaps and write environment adaptive code and verify passes permissions as early as possible. Here are some possible research work we suggest. Platform can provide a local simulator integrated with IEE to help avoid the to reserve access environment. Platform the useful. Conductive studies are as of production and suggest possible and tools for due to the time limitation can our work. Thank you, everyone.
Thank you, Ru, for great presentation. I think at the end we had some glitches, but that was fine. We have a couple of questions for you. Are you aware of any studies of the environmental impact of defect in deep learning jobs regarding the, for example, CO2 emission? And this question is by Andrea. unfortunately, we could not hear you well. Maybe this is only a problem from my side, but I could not hear your answer. I'm so sorry about that. So maybe the connection is not great. So I'm going to ask the second question. Many of the failures seems to be of the cloud computing variety. How do your results compare to prior empirical work on cloud failures?
We also compare to empirical work on cloud failures, but our work has a lot of difference because the subjectivity of our study is deep learning jobs and the program failures of them.
Right. I have also myself a question for you regarding your work. Basically, from what I saw in the presentation, so you talk about memory, out of memory or other kind of memory failure. Have you noticed any particular kind of category related to memory leaks in deep learning job? Because I personally observed many of these kind of bugs in deep learning systems. Do you have any comment about that?
You mean the GPU out of memory errors in our study?
No, in particular, I mean memory leak, the kind of leaks that due to many reasons, either configuration issues or basically bad practices in the code, resulted in any sort of leak in the memory.
Okay, thanks for your question. Actually, memory leak is not a problem we can find. It's a problem users may resolve it locally. Actually, the problems caused by memory leak is often caused by the code in the deep learning framework. It's not caused by the user code. So the use the deep learning frameworks to write their models, and then they will local test their models. They can find it. So it's not in our study scope now. Thank you.
Mm-hmm. Thank you for your answer. So I think we are at the end of our session. So let's conclude this exciting session. Thank you very much for the audience, for the presenters, and the virtualization team. You all did a great job. Thank you very much.
Thank you for sharing, and good night.
Good night.
Thank you.